So we're going to do some example problems here today over Newton's laws. So let's just dive right into those. I'll point out, of course, that the only real formula that we have here, at least right now, is F equals ma. But this is an incredibly powerful formula that we will use over and over again this year, because we have lots of other formulas that we'll use to solve for a force. And we can always set those formulas then equal to the ma part of the equation here, the ma, and so this comes up over and over again. And again, technically there is a W equals mg version of this, where we are taking the special case of the acceleration due to gravity to calculate an object's weight. And of course that really is just the force due to gravity. And of course, if we're here on Earth, that g is always 9.81 meters per second squared. What force is experienced by a 450 grams, of course, is a mass, soccer ball if it accelerates at 2.5 meters per second squared? And we wouldn't have to be told accelerates here because, again, the units tell us that, but this just means that we're going to use F equals ma. However, before we can do that, remember that we are using a special case of the metric system called the MKS system, where our masses are always in kilograms. We don't use the grams base, we use the kilograms prefix on it. So we need to turn this into kilograms, and that's simply move the decimal 1, 2, 3 here to the left to turn grams into kilograms. You could also divide it by 1,000 because there's 1,000 grams in a kilogram. But anyway, that gives us 0.450 kilograms for our number there. So then from there, it's mass times by the acceleration. And then it's just punch those two into a calculator. And I get 1.125, and that would be kilogram meters per second squared, perfectly acceptable unit. However, we generally will combine those into a Newton, and plural, of course, newtons. And then we need to check sig figs here. So we have 3 in the original value given there and 2 here. So we're going to have 2 in our final answer. So that's going to come out to be 1.1 newtons for our final answer here. Now, the next one that I have here is actually one that I forgot to type up, but I want to make sure that we get a chance to practice with each of these formulas. So what is the weight of the ball? So weight is simply m times g, where, again, weight is really just a special case of the force due to gravity. So m times g, the mass we've already figured out is 0.450 kilograms, and the acceleration due to gravity 9.81 meters per second squared. And so now let's just punch those into the calculator. And the nice thing here is I can just come up here and second enter, or on some of the newer, the 84s, you can come up here and move your cursor up here. It will highlight the whole equation, hit enter, and it will retype it there. And then all I have to do is change my acceleration. Saves me a little bit of retyping. Anyway, and then we're going to have the same number of sig figs here because the acceleration due to gravity is considered a constant, and so we're not going to let that limit us. We're not, because we have 3 sig figs here and we didn't use this value, so 3 sig figs this time. Anyway, rounding that one off to 3 significant figures, I end up with 4.41 newtons for the weight of the ball. Next, we're asked what is the acceleration of a 1,300 kilogram car, that's our mass, that experiences a 200,000 Newton force when colliding with the pole. And then there's a second question here, which we'll come back to in just a moment. We're going to again use F equals ma, but this time we're solving for a, so we're going to leave a alone and we'll plug in our other values. And then, of course, it's just basic algebra to rearrange that and get a. And so a is equal to that, and I've got 1, 2, 3, 4 sig figs there, and I have, looks like 6 there, so I'm going to round this one off to 4. So that would be 153.8. Units here are a little bit trickier because you have to remember back in the back of your mind that a Newton is an abbreviation for kilogram meter per second squared. And if we divide that by a kilogram, or that would be the same thing as multiplying it by a 1 over a kilogram, then you can see that the kilograms here are going to cancel out, and we're left with meters per second squared. And this is that dimensional analysis thing where we're letting our units help us check our answer, because if our units come out right, then our answer is going to be right. Yes, you know an acceleration is going to be in meters per second squared, but how do you know you didn't make a math mistake? Well, if you take the time to do the math with the units and the units come out properly, then odds are you did the math properly. And so that's the purpose here. And unfortunately, when we have these combined units, you have to remember what the underlying fundamental units, the base units in the metric system actually are, because all of our combined units are some kind of combination of those fundamental base units. Anyway, this gives us the acceleration. And now we're asked how quickly did it come to a stop if it was originally traveling at 18 meters per second. Well, for that, we can go back to our kinematic equations, and so those don't go away. They're still useful, but velocity final is equal to velocity initial plus a times t. Well, the velocity final, if it's colliding with the pole and comes to a stop, that really is code for velocity final is 0 meters per second. So then we know that's 0 meters per second. The velocity initial is what this 18 is. And so then that's going to be 18 meters per second plus the acceleration we now have, 153.8 meters per second squared, and time. Now I can see here that this isn't going to work out, or I'm going to get a negative time, which doesn't really make sense. And it turns out that because this thing is slowing down, really what we're saying is it's a negative acceleration. And this probably should have said a negative force up here. But what you might call a deceleration is what we would call a negative acceleration. So anyway, there we have that. So now rearranging this, I'm going to move the 18 over here. And then to get the t alone, divide both sides. And now I'm going to punch that into a calculator. So 18, actually, the negative divided by negative is going to cancel out, so I'm not going to worry about putting in those signs there. I get 0.117 seconds. And again, just checking the units here, meters per second divided by meters per second squared, we're going to be left with a 1 over 1 over seconds, and that will rearrange to. And since our velocity initial had 3 sig figs, our velocity final at 0, that could be an infinite number there really, and our acceleration here had 4, and was based off of that original mass, we're going to have 3 sig figs for our final answer, because the velocity is the limiting one there. And so that is equal to our time. These here aren't really calculations. These are getting into some of the Newton's third law type of questions that you could have. So the horse cart problem, where the horse is pulling forward on a cart with a force of 413 newtons, and is asking what's the other half of the action-reaction pair. It's one way it's sometimes worded. Well, for every action, there's an equal and opposite reaction, equal in size, opposite in direction. So the equal and opposite reaction here is that the cart pulls the horse backwards 413 newtons. Or we could say negative 413 newtons, because forces are vectors acting on the horse from the cart. Of course, I mentioned in the notes here, how can the horse go anywhere if these two cancel out? And the answer is there's more. The horse isn't just pushing against the cart. Here, the forces do cancel out, but we also have the horse pushing against the ground. And since the horse and the ground aren't tied together, for every action, there's an equal and opposite reaction. So when the horse pushes against the ground's going to push the horse forward. Same thing's happening here in the wheels. It's a little bit more complex when you have a rotational system, but in the end, the wheels are pushing down and backwards on the ground, and so the ground pushes the wheels forward. And so you have other forces going on here. On our other one here, a book pushes down on a table. We always like to draw diagrams for these. And so the book is pushing down on the table. And so what's the equal and opposite reaction? The equal and opposite reaction is that the table is pushing up on the book. Now, those aren't the only forces going on here. The book experiences two forces on it, and that is the weight of gravity, or force due to gravity, excuse me, and it feels a support force or a normal force coming from the table. Those two happen to be equal in size and opposite in direction, but they are not, let me repeat that, they are not an equal and opposite pair because they're both acting on the book. Action-reaction pairs are always A acts on B, and then B acts on A. In this case, it is the book pushes on the table. Equal and opposite is that the table pushes on the book. Equal in size, opposite in direction. So even though we have a pair of forces here, this is not our action-reaction pair. The table also has other forces acting on it. It has the weight due to gravity, or force due to gravity. It has a support force from the floor, and it has this compression, this weight on it from the book. And so there's a force from the, and so there's other forces going on. But be careful. A lot of students want to say that this here is an action-reaction pair. It's not. They do happen to be equal. They do happen to be opposite, but it is a coincidence there, or a result of other physics going on. They are not the action-reaction pair. This is not Newton's third law being illustrated here. Anyway, we're actually going to get into doing force diagrams and then using force diagrams to do calculations in the next video. So be sure if you have any questions that you let me know.